Okay, so here are the notes for section 3, binomial probability distributions. So a binomial probability distribution results from a procedure that meets the following requirements. The procedure has a fixed number of trials, so you don't go on forever. Trials must be independent, meaning the result of one does not affect the result of the next. Each trial must have all outcomes classified into 2 categories, typically success or failure. The probability of success remains the same in all trials. So you can't, if you're rolling a die, you can't change, from a 6-sided die to a 10-sided die to a 20-sided die. If you're flipping a coin, you can't switch from a fair coin to a weighted coin or things like that. Okay. So just some notations. Sorry, get it in there. So S and F, success and failure, denote the 2 possible categories. So P of S is represented by P, probability of success. Q is used to represent the probability of a failure. Note over here that since only 2 things can happen, if you know the probability of success, 1 minus that is the probability of failure. N is how many trials you're running. X is the specific number of successes in N trials. So X is any whole number. So 1 success, 2 success, 3 success. P, probability of success in 1 trial. We talked about that up here. Q, same thing, probability of a failure. P of X, the probability of getting exactly X successes. So if you see at least or no more than, you're going to have to add up a bunch of values together. Now, down here, the word success doesn't necessarily mean a good thing. It can be just usually the thing you are looking for, not necessarily a success. So example 1, when an adult is randomly selected, there is a 0.85 probability this person knows what Twitter is. Suppose we want to find the probability that exactly 3 of the 5 random adults know what Twitter is. So does this procedure result in a binomial distribution? So the criteria were fixed number of trials, 5. Each trial is independent. We did with replacement. Each trial must have all outcomes classified in 2 categories. They either know what Twitter is or they don't. The probability of success remains the same in all trials. So since it's randomized, yes. So this, yes, it meets all the criteria. This procedure does result in a binomial distribution. Identify the values of N, so that's the number of trials, 5. X, we are looking for 3 of them. P, probability of success, since we're looking for people who know what Twitter is, that's 0.85, which means Q, the likelihood they don't know what Twitter is 1 minus that, or 0.15. Down here, didn't print again for some crazy reason, the binomial probability formula. So the probability of getting however many you're looking for is n factorial divided by n minus x factorial times x factorial. This is a combination right here. P to the x is the likelihood of success raised to the number of successes that you need. Q to the n minus x is the likelihood of failure raised to the remainder of the items. So for this example up here, x would be 3, n minus x would be 2. So there's 5 people total. I need 3 successes and 2 failures for x starting at 0 going up to n. Okay, so example 2. Given that there is a 0.85 probability that a randomly selected adult knows what Twitter is, I'm getting exactly 3. So my formula, the probability for 3 is n, so there's 5 people, and then it's n minus x, so that's the difference, so 5 minus 3, so 2 factorial, and then x, so that, times the probability of success, I want 3 of them, times the probability of failure, which I need 2 of. Note these exponents should add up to however many trials you have. So since I have 5 people, 3 plus 2 is in fact 5. So that's a quick way to check to make sure your exponents are correct. And all these are numbers, so it can all just go in my calculator. So let's see how I can do this. Okay, so 5 factorial divided by 2 factorial divided by 3 factorial times 0.85 raised to the third times 0.15 raised to the second, and math happens, and out comes this number. So the likelihood is 0.138, so 13% chance of randomly selecting 3 adults who know what Twitter is if there's a 0.85 probability that any one adult knows what Twitter is. Okay, so example 3, 60% of adults believe in the devil, so we'll call that our p-value, believing in the devil, which means Q is 0.4. If we randomly select 5 adults, so N is 5 again, find the following. probability that exactly 3 of the 5 adults. So it's going to be similar to this setup. The only difference is my probabilities are different. So the probability that 3 people selected at random from 5 believe in the devil is the number of people you're surveying, the difference, so 2 factorial, the number of people you're picking, 3, times likelihood of success, 0.6, and I need 3 people to believe in the devil, and then the probability of failure, 2 people aren't going to. And that all goes in my calculator again. So 5 factorial divided by 2 factorial, whoops. Oh, now I've done it. There it is. Divided by 3 factorial times 0.6 raised to the third times 0.4 raised to the second. So this comes out to be 0.346. So about 1/3, 35-ish% chance that exactly 3 adults. All right, so down here at the last one, find the probability that the number of adults is at least 2. So 2 or 3 or 4 believe in the devil. Now, so that means I have to find the probability of 2, probability of 3, probability of 4, probability of 5, and add them all up. Or I could find the probability of, so there's 2 options. P2 plus P3 plus P4 plus P5, or 1 minus P0 and P1, because I don't want those 2, so I can subtract 1. I'm actually going to do it the short way and find P0 and P1, because that means I have to calculate fewer things and then subtract them from 1. So for P0, 5 factorial, so the difference is 5, 0, 0.6 to the 0th, because I don't want anyone to believe in the devil, times 0.4 to the 5th, because I want everyone to not. And then P1, 5 factorial, difference is going to be 4 factorial, 1 factorial. Notice these 2 numbers should also add up to the number on top. So 0.6, I need only 1 person to believe, and I want 4 people to not. So in the first case, 5 factorial divided by 5 factorial divided by 0 factorial times 0.6 to the 0th times 0.4 to the 5th. This guy is 0.010. Then I change to the other formula. And I get 0.015. So 1 minus 0.010 plus 0.015. So that's 1 minus 0.025, which is 0.975. So it's about a 0.975 chance that 2 or more will believe in the devil. There's at least 2. So 2, 3, 4, 5, so on and so forth. So that is the end of this section.